All right. All right. So we're up to chapter 3 here, and this is a classification task. And this goes along with a hands-on project like before, where we're going to train a classifier. So I'll talk about the concepts here and then I guess go to the hands-on part. Um, we're going to use this data from the MNIST. This is from, I think, the US Census. They recorded handwritten digits by census takers, and we're going to label them. So each one of them is a 784 pixel image in grayscale, and it's just a digit from 1 through 9. And as you can see, because they're handwritten, they're sort of different, and some of them are tilted over, and some of them are a little distorted. So this is a good machine learning vision, computer vision task to categorize things. So you break them into training set and test set, 60,000 images to train on, and 10,000 more images to test your AI on. And then for starters, we're instead of sorting it into all 10 categories, we're going to make a binary classifier that just decides whether it is a 5 or not a 5. So you just accumulate the data on that ground. And now you can make a model. So you preed the input image, you take all 784 pixels and treat them as independent bits of data and feed them in as pixels, and then feed the output to a neuron. So this is a very simple model, and it's going to use stochastic gradient descent to adjust these parameters to try to find the best border that will separate 5s from not 5s. And so this is what will do that, a stochastic gradient descent classifier. It will just randomly assign values to the parameters and then take steps into to decrease the error. And so it's going to train it on those 60,000 images and see how many it got right and take the number it got right as a measure of success. And you can see the prediction for the first 3 images here. So you'll see the prediction here was 0. It's a 5, which is true. This one is a 1, so that is not 5, and it correctly predicted false. This one is a 2, and that correctly predicted it was false. So it got the first 3 right. And now, the interesting issue of how do you measure the performance of a classifier? And there are several different ways to do it. This is one using cross-validation where you use folds. So you fold the data into 3 folds. You train the model 3 times on 2/3 of the data, and each time you train it on 2/3 and evaluate it on the other third. So there are 3 ways to do that. So now you get the accuracy. Here's the accuracy of those 3 things: 95% right, 96% right, 96% right. So that's a number. Now, that might sound good, but remember, since 90% of the data is not 5, if you just labeled every one of them not 5, you'd be 90% right. So 96% right is not as impressive as it probably sounds. Yeah, let's see here. All right. So to get a more thorough explanation of the quality of your model, you can make the whole confusion matrix. So the first row is the false images. This is the false images correctly found as false. Here's the false images incorrectly found as true. And here's the true images incorrectly found as false, and the true images correctly found as true. So you can see it has a small chance of taking things that are not 5s and calling them 5s, and it has a pretty large chance of taking things that are 5s and calling them not 5s. So that's a better measure of the more thorough measure of the performance. And there are some other measures. Precision is true positives over true positives plus false positives. That's another, it gives you a number here, 83%. And recall is true positives. That's precision. But you can get a perfect precision by classifying everything as false and having only one thing you found true, because it doesn't make any mistakes. So that's one measure. Another one is recall, which is true positive or true positive plus false negative. And that measures the ratio of positive instances that are correctly detected. So what it means is there are different measures. All right. And so you can adjust these by adjusting a threshold. So for example, here's a group of images. Here it calls all of these not 5 and all of these 5. So these are the mistakes. This 6 it thought was a 5, and these 5s it thought was not a 5. So you can, in this case, you can adjust these things. That just shows you what the various concepts are. And so you can make an F-score where you combine the precision and the recall. And this will be high only if both precision and recall are high. And even more, you can adjust the threshold. What happens is it has an actual number, which is the strength of the signal. And if the strength of the signal is above a certain value, it calls it true, which would be a 5. If it's below that, it calls it not 5. And you can adjust that threshold. So if you put the threshold very high, then it will almost never call anything that is not a 5, but it will start calling a bunch of 5s not 5s. And that it makes your precision greater than your recall. If you make it low, you have the opposite situation, and there's a central point where precision equals recall. And this, if this may seem familiar, if you take it Security Plus, the same thing is true of biometric systems like fingerprint identification. You can make your fingerprint identification system very, very sensitive, so it will reject the right finger very often, but therefore almost never letting people with the wrong finger. Or you can make it very tolerant, where it will not reject the authorized people, but then it will let in more unauthorized people. It's very much the same issue. All right, and so you got this trade-off, and you can see it here as you go through various levels. And if you set your threshold all the way up here, you will never have false positives. You'll never call anything a 5 that's not a 5, but you'll have a lot of false negatives where there's a bunch of 5s that you incorrectly called non-5s. Anyway, and so you can graph the effect of the threshold on precision and recall and see the various things. And there's a curve here. There are various ways to plot it out. And this thing's called the receiver operating characteristic curve. And the area under the curve is the quality of your classifier. So if it's way up here, that's a very good classifier. If it's way down here, it's pretty bad, like a random classifier. Okay, and you can compare various models. Here's what a random forest, and here's a single stochastic gradient descent. So we talked about this before. A random forest uses many classifiers and averages them together to make less errors. And as you can see, it can do a better job. All right. So I've got some Kahoots. I guess might as well try these. We'll see if people like them. Let me get to my right browser for these, and it's this one. All right, and I've got to log in and get to my chapter 3A Kahoots. I wonder which account I'm logged into. Let's see. Oh, good. Okay, this is the right one. So 3A is somewhere down here, and there it is. All right.
It's 11 o'clock.
How do I get to the link to this?
You go to kahoot.it, and then
Okay.
you type in this number. Good.
Okay, thank you.
It's Italian.
Okay.
At least I assume it's Italian. I guess IT might just be a new top-level domain. All right, I'll wait a few more seconds. I think people are still coming in. All right. All right. So a simple, efficient way to train models. Yeah, stochastic gradient descent is the process we've been using, where you make all these little steps adjusting the parameters to make the error smaller. So these are not ways to train models. These are types of models, and that's a type of data. But this is the process, the simplest, most common process, where you make many small steps changing the parameters. All right. So which performance measure displays all the false positives and the false negatives? Yeah, that's the confusion matrix, gives you all the information, shows you how many were correctly identified as true and correctly identified as false, and both kinds of errors. All right, what measure is high only if both precision and recall are high? That's F1, the statistical measure, which is really more of a measure of the actual quality of your system. All right, if you can do both jobs, correctly identifying true instances and correctly rejecting false instances. All right, which one is 0.5 for a random classifier? That's the area under the curve. They had that there. That shows a random classifier will still get half of them right, of course, but a good classifier will get more than half of them right. All right, so there are the winners. MD is the winner, obviously. All right, anyway. All right, let's go on back to here. All right, and there's the area under the curve. This is the false positive rate and the true positive rate. And a perfect classifier would be right up here, a random one here, and a realistic one somewhere in between. All right. So the classifiers we've done so far only do a binary decision. Something is true or false. But of course, in realistic things, you want to separate things into more categories than that. And for this data, we want to make 10 categories for each of the possible digits. So to make that, you have to somehow combine binary classifiers to do it. So one way to do it is with 10 binary classifiers, 0 or not 0, 1 or not 1, and so on to 9 or not 9. And so each, you could choose the classifier that has the highest decision score. So just find which one of these 10 gives you the strongest true signal and call that the category. That's one way to do it. That's another way to do it is 1 versus 1, 0 or 1, 0 or 2, 0 or 3. So you're actually going to have like 45 possible classifiers, and you have to combine all these together. You could select the digit that wins the most duels here, where the most of them find it true. So this is a way to do it. Each classifier is only trained on those 2 digits. You don't show it the other digits. And so this is one way to do it. Most of the time, the one versus the rest is considered preferred, but you can do it either way. All right. Now, so here we're going to use 1 versus 1 and a support vector machine, which is a machine we'll talk about in more detail later, but it draws a straight line through parameter space to separate the 2 categories. And so this will run 1 versus 1. And so you see scores like this. And this one here, the classifier scores are highest for 5. This is it a 0 or not a 0? And its strength of it being a 0 is 3. This is a 1, 2, 3, 4, 5. The 5 says it has a 9 strength for 5 being true, and that's bigger than all the others. So you would call this thing a 5. All right, and you can also do 1 versus the rest. And again, you'll see in this case, it incorrectly predicted 3, but 5 was almost as strong. So this is 0, 1, 2, 3. Most of them are negative, but this one's plus 1800. And this minus 1386 is the next biggest one. So it's just an example of seeing some of these run. All right, and so to analyze your errors, you can make the confusion matrix of a multi-class classifier, and now it's a 10 by 10 grid. So here's the predicted label and the true label, and the diagonal are the ones that are correctly classified, and here you see all the various types of errors. Now, 5 has a low number of images. 5, 5, let's see. I'm not understanding this thing. I'll count of images. Okay. And so yellow is stronger. I see 5 has less total images correctly found here. That's right. So if you just compare the raw total, it found like 5,400 1s and 5,200 2s, but only 44 5s. So they might think that its ability to detect a 5 is very low, but it might just be there aren't as many total 5s in the data set. So it would be better probably just use percentages. And now you'll see what percentage were correctly identified. And again, you can see, in fact, it is true that 5s have a low percentage, lower than the others, which I think reflects the fact that 5s are more easily confused with some other numbers like 8 or 9. And you see that here. If it was really a 5, it had like a 10% chance of thinking it was an 8, which makes sense because they look kind of similar. All right, and you can normalize the rows various ways, and you'll see that, in fact, a lot of things are mislabeled as 8. So apparently there are quite a few digits which, when sloppily written, are misinterpreted as looking like an 8 by the model. All right, and you can look at it other ways. And you can view example images too. So if the upper vertical line of a 3 is shifted to the left, the model will tend to call it a 5. And so here's the images that were really a 3, but interpreted as a 5, and you can kind of see why. This does look a little bit like a 5 more than a 3. If the first loop is sort of to the left, it makes sense. And so if you made the model, to make this model more robust, you'd want to do something like adding shifted and rotated images to the training set. And you might do what we were talking about late last night, DNN, where you sort of combine neighboring pixels to get more generalized features than just expecting this particular pixel to be dark for a 3. All right. And so that's multi-label classification, sorts them into categories. You can apply labels. And there's also multi-label classification, where the same input can have more than one label. So you might be putting labels on images, like it's a dog, it's outside, it's near water, and one image could have all 3 of those properties. So you can define multiple labels, and you can decide whether a digit is large and whether it is odd, and it could apply both of those. And so to evaluate those becomes a somewhat more complicated statistical task. All right. Stochastic vector machines don't natively support this, but you could use various ways to combine smaller models to achieve this task. And then there's multi-output classification, where you're going to have each label can have more than two possible values. So if you're trying to remove noise from images, this is a much more complicated task where you somehow have to decide whether the pixel, you want to turn this into that. So you're trying to modify it. And it's not as simple as just choosing something, whether this is a 7 or not. But that technically is a classification task. It's technically classifying what part of this image is noise to be removed and what part of this image is signal to be preserved. So there's that. Now let's try another Kahoot. Let me find them, which should be, here they are, good. That's 3B. All right. All right. Maybe we got everybody that's coming. All right. All right. So which system outputs either a 5 or not 5? Is this one. These are both ways to make multi-category classifiers. This is a binary classifier, and that's not one versus the rest or one versus one. All right. All right. What system uses smaller training sets for each binary classifier, which would mean less total computing time? All right, that's one versus one. Of course, you just have the zeros compared to the ones and you ignore 80% of the data. All right. One versus the rest always uses all the data. So it would be 0 compared to all the things that are not 0. All right. All right. Which system can apply several labels to each image? All right, that's a multi-label classifier. The name is pretty descriptive. All right. All right. All right. Let me stop this recording.